Amagi is far outside the small star belt, located between Saturn and Neptune. It travels alone in the dark and cold edge of the solar system. Its axis of rotation is extremely tilted, almost lying on its orbit. This unusual step has long puzzled astronomers and spawned countless theories. The planet was first discovered by British astronomer William Herschel in 1781. Uranus was the first planet discovered through telescopes, a discovery that expanded human understanding of the boundaries of the solar system. For hundreds of years, the distant planet was nothing more than a faint point of light in telescopes, like a blue ghost orb. But now, with the advent of the James and Webb Space Telescopes, the exploration of Uranus has ushered in a new chapter. With its unprecedented observation capabilities, the Webb telescope has gradually unveiled the layers of this weapon, revealing a beautiful and complex world. On the journey of human exploration of the universe, the Webb Space Telescope is like a watchman. It is the crystallization of engineering technology and a symbol of human beings' endless thirst for knowledge. This telescope is the successor of the legendary Hubble telescope and is equipped with advanced observation equipment. The main mirror has a diameter of more than 6 meters. Designed specifically for observing the infrared spectrum invisible to the human eye. Infrared spectroscopy allows it to penetrate cosmic dust clouds, discover distant galaxies, and study the atmospheres of western outer planets. The launch of the Webb telescope was also a great achievement in itself. Carrying an Ariane 5 rocket, it flew about 1.5 million kilometers and reached the second Lagrange point between the Sun and the Earth. A stable space with almost no interference from the Earth and the Sun, allowing it to better observe the universe. The observation capabilities of the Webb telescope are not limited to the ancient universe and distant galaxies. It also played an important role in unlocking the mysteries of the solar system. Its powerful instruments, such as infrared-only cameras and mid-infrared imagers, revealed new details about many planets, moons, and other celestial bodies. Take Uranus, for example. In the past, our knowledge of this distant planet was limited to blurry images taken by the Hubble telescope and others. Now, with the help of the red and white observation capabilities of the Webb telescope, we get to see Uranus in a whole new light. The high sensitivity of the Webb telescope allows us to clearly observe Uranus's atmosphere and weather patterns, even its mysterious ring system. By analyzing the spectrum of Uranus, the Webb telescope can decipher the composition of its atmosphere, detect the presence of gases such as methane and hydrogen. This not only helps us understand the current situation of Uranus, clues to its formation and evolution are also provided. James, the Webb Space Telescope continues to exceed expectations. New details about the universe are revealed to us almost every day. Its latest achievement is a new set of images of Uranus, even surpassing the stunning observations in April 2023. Early 2023, the Webb telescope has allowed us to see Uranus's atmospheric dynamics and ring system with unprecedented clarity. The latest images go a step further. Not only is it clearer, it also revealed previously unobservable details. Using the rings of Uranus as its force, the latest images show even more surprising structures. Even capture Chandai who had not picked up before. For example, the extremely thin sea ring closest to Uranus. The advantage of the Webb telescope is not only one-time observation. It also lies in its ability to continuously track changes in celestial bodies. Continuous observations of Uranus allow us to track changes in its atmosphere, record the movement of clouds. Even the long-term evolution of the storm was observed. In particular, the changes in the polar regions of Uranus are particularly eye-catching. The bright white tops and dark bands near the poles have changed significantly in recent years. These ongoing observations provide valuable data for understanding Uranus' seasonal changes and long-term climate patterns. Among the planets in the solar system, Uranus stands out with unique characteristics. The angle of its rotation axis is about 98 degrees, almost parallel to the track surface. Uranus is almost lying on its side and rotating on its axis. Has long fascinated astronomers, piqued their interest in exploring its causes and effects. Scientists speculate that, in the early days of the formation of the solar system, Uranus' clear angles are not so exaggerated. The mainstream theory holds that what could have been a catastrophic collision maybe a collision with a planet-sized body, completely changing its direction of rotation. This huge impact not only changed Uranus's axis of rotation, and its entire system, including satellite and ring systems, left a deep mark. This unique spin causes Uranus poles to alternate between being bathed in sunlight or plunged into darkness every 42 years. This extreme clear angle brings extreme seasonal changes. Seasons are very different from those observed on other planets. For planetary observation and research, the unique perspective that this clear angle brings is crucial. It allows us to observe Uranus rings and moons from different angles, revealing its composition and dynamics. For example, when the rings of Uranus are facing the Earth, the ring is almost completely invisible. This exposes darker sinking bands and smaller moons. In contrast, the Earth's rotation axis is only 23.5 degrees, and Uranus's extreme angle caused significant meteorological changes, making it a valuable object for planetary climate research. This clear angle also affects the circulation of Uranus's atmosphere. Long-term exposure of polar bodies to sunlight can create complex weather systems. The latest images taken by the Weibo telescope show. It provides a unique experimental place for us to understand atmospheric physics. Let's walk through the year of Uranus together. Since Uranus takes about 84 Earth years to orbit the Sun, so each of its seasons is equivalent to 21 Earth years. Since then, each hemisphere experiences long days and nights, leading to dramatic changes in the planet's surface and climate. One of Uranus' poles spends decades-long summers in the Sun. The other pole is plunged into a long winter. This strong contrast brings unique atmospheric conditions, forming complex meteorological systems and climate changes. These seasonal changes have profound effects on Uranus' atmosphere. When sunlight shines on the planet's surface, the atmosphere will be heated, forming huge storms and active cloud systems. These phenomena are not static. Instead, it continues to evolve with the changes of the seasons. Paint a picture of Uranus' ever-changing landscape. The most striking thing is the bright cloud tops. When the sun hits Uranus' atmosphere, these clouds, made of frozen methane and other gases, reflect sunlight, forming a gorgeous landscape. And dark storm areas roam the planet's surface like giant hurricanes. Also, the seasonal phenomenon of Uranus not only affects itself, it also affects its satellites. A recent study found that Uranus satellites will form temporary atmospheres under certain conditions. This phenomenon is closely related to the unique environment of the Uranus system. The key to the formation of these temporary atmospheres is Uranus's extreme rotational angle and its effect on the orbits of its satellites. As the satellites of Uranus orbit the planet, experience long periods of intense sunlight alternating with long periods of darkness. During the long summer, the frozen surface of the satellite will undergo sublimation. Directly from solid to gaseous state, a thin temporary atmosphere forms. These atmospheric layers are most pronounced when the satellite is at its warmest. Recent research shows that these atmospheres are more complex and varied than previously thought. Uranus's satellite rings are often overshadowed by the spectacular rings of Saturn. Recently, to Uranus, comparative studies of the rings of Saturn and Jupiter reveal these relatively unknown, but equally fascinating celestial features. Unlike Saturn's broad and bright ring system, the rings of Uranus are narrow, dim, and limited distribution, extended to within 4 planetary radii, including some rings that are difficult to observe, such as the female ring and the angry ring. The study deeply explored the gravitational influence of Uranus's main satellites on the ring system. This factor plays a key role in the formation and evolution of rings. The 5 main satellites of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, more massive than other small satellites, dominates the gravitational structure within the Uranus system. Their masses and positions provide important information for our understanding of Uranus moons and the ring systems their gravity creates. The formation of Uranus rings is thought to be the result of multiple processes, including collision, satellite fragmentation, and gas release from the main satellite. These dynamic processes affect the material composition of the ring, and driven by the changing environment of the Uranus system. The stability of the ring system is closely related to the gravitational interaction of the satellite. The study also explored the attack process of substances within the ring system, and the important role of the Shepherd satellite in the maintenance of the ring system. Uranus rings also provide us with a unique opportunity to study the planet's internal structure through seismology. The model results show that the gravitational interaction of the satellite with the ring system can lead to significant loss of material within the ring. The complex interactions of these satellites with the ring system, especially the resonance phenomenon between satellites, provides key clues for understanding the long-term evolution of the system. The mystery of Uranus is not limited to this. As we all know, there are auroras on the Earth. Uranus also has auroras. However, its auroras mainly appear in the infrared spectrum. Observation through a thin telescope. Astronomers have detected enhanced radiation from the trihydroxide ion H3+ in the atmosphere of Uranus. This is a groundbreaking discovery. Help reveal Uranus' unique magnetic field and atmospheric dynamics. Uranus's magnetic field is severely offset from its rotation axis. A unique magnetic layer is formed. The ionosphere and thermosphere are coupled. Observations of these infrared auroras are critical. This opens a new window for LISHAN to explore Uranus's magnetosphere. The infrared auroras of Uranus show significant differences from those of Jupiter and Saturn. On Jupiter, the lifetime of lit triple radiation is shorter, making the changes in ultraviolet radiation more stable. The brightest infrared radiation of Uranus does not necessarily match the brightest ultraviolet radiation of other planets. This auroral feature provides us with rich information about planetary atmospheres and is particularly beneficial to the study of icy exoplanets. In-depth studies of Uranus auroras have shown that hot spots near the aurora borealis are not caused by rising temperatures, but by increased electricity caused by auroral activity, which plays an important role in heating Uranus' atmosphere. By studying this unique phenomenon, we can better understand how auroras affect the atmosphere in